Fancy model would be nice, yeah. Now I want to talk about the questions on the midterm. The first two questions are mostly Ed's doing, and so I'll let him talk about those next time when he discusses it. The last two questions are my fault, so I should be required to come up with an answer for those at least. Question number 3 has to do with drawing a sphere. The idea being that you have a primitive element, which is a unit sphere sitting at the origin, which can be expressed in the notation of the quadratic surfaces that we did as this matrix with all the ones in it, and a -1 in the lower right-hand corner. And this thing is positioned someplace in a viewing space out in front of the eye somewhere. And so we have the eye like this, and the sphere is out there being looked at. And there's a transformation matrix then that transforms this sphere into the viewing space. And the transformation matrix also includes perspective projection. So strictly speaking, the eye now is at minus infinity in the z direction. So 0, 0, 1, 0 is the coordinates of the eye. Yeah. Well, homogeneous coordinates, any non-zero multiple of this thing is the same point, so right? Well, minus infinity and plus infinity are the same place in this projective geometry. So there's a transformation matrix T, which is used to view this thing. Now, if you want to get then the sphere in the viewing coordinate space, you have to say T inverse times this times T transpose inverse. This then will be a 4x4 matrix, which represents the sphere in the viewing coordinate space with the eye at minus infinity in the x direction. And it's going to be basically squashed down a little bit and probably turn into an ellipsoid. And the eye is back here at infinity. Now, if you're going to go and draw this thing with a line drawing display or even a shaded image display, you just transform all the points into viewing space and draw them in. But it turns out there's an interesting trick that you can do. If you happen to have a hardware system that does clipping on the far clipping plane, or a software system for that matter, there'll be this view box here that goes, say, plus and minus 1 in the y and the x direction, and either 0 to plus 1 in the z direction, or minus 1 to plus 1, depending on how you want to tie it up. And so the hardware or the software is going to clip away everything that's outside of this volume. Generally, the sphere is going to be transformed into some place in that volume. But if you go to draw it, you're going to get the back parts of it as well as the front parts. There's a wire mesh wire line drawing. But given the fact that we have this clipping thing already, if you do something to this sphere, it's possible to take the silhouette plane of the sphere and to make it coincide with this far clipping plane. So then if you start feeding lines through the clipper, any lines that are on the back half of the sphere are going to get clipped off, and anything on the front half of the sphere will still show up. So the question was, how do we take the silhouette plane of this thing and make it match up with the far clipping plane without changing the appearance of the image any other way? Okay, first of all, what is the clipping plane? One of the results that was mentioned in the talk on second-order surfaces is that given a second-order surface, if you want to find the silhouette plane of that thing, all you have to do is multiply the coordinates of the eye point by the quadratic surface that's the object, and the result then is going to be the equation of the plane that's the silhouette outline of this thing. So in homogeneous perspective coordinates, this is where the eye is. You multiply this by the 4x4 matrix Q, and that's this T inverse times 1s times T inverse transpose. And you'll get 4 numbers out. Actually, what you're going to get is the third row of this matrix. These 4 numbers can be thought of as the coefficients of the equation of the plane that you're interested in here. You actually have to transpose it, tip it on its end to make it look like a real plane. Like that, right? Now, in order to change this plane into the plane that we want, which is the back clipping plane, that's the equation of the plane z equals 1, 0, 0, minus 1, and 1. In order to change this into this, without changing the x and the y or the w, if we touch those, we're in trouble because it's going to change the appearance of the sphere. The only thing you can do is change the z coordinate. We're going to do a skew transformation in z. We're going to slide, things back and forth in z without changing the x's or the y's any. It's like you have a stack of cards and you move them back and forth, right? Better watch out I don't reuse the same symbols here. This, in general, is the matrix for a skew transformation in the z-axis. That means if we multiply any point times this transformation, we're going to get x and y, some gibberish, and w out here. X and y and w don't change, so that means the appearance of the image on the screen is going to be intact. It's just the z depth that's going to get played with. So what we want to do is to find out what p, q, r, and s it will take in order to transform this plane into that plane. How do you transform a plane? You multiply the plane thing by the inverse of the point transformation matrix, right? So we want to, first of all, take this matrix and symbolically invert it. I did this here. Need to make sure that I don't, yeah. This, symbolically, is the inverse of that matrix. So you multiply this skew transformation times the point that we got, the plane, ABCD. That's the old silhouette outline plane. And we want to get that plane. You now have 4 equations, and you can solve for these numbers p, q, r, and s from those 4 equations. Once you have p, q, r, and s, you put them in this matrix, and this is a matrix which is the skew transformation in z, which you must apply after the perspective has been done in order to skew this plane back into match up with the far clipping plane. So then we have the net transformation matrix that we would be using to view things would be T, what we started out with, times this skew in Z, P, Q, R, and S, is multiplied on the right of the transformation matrix. So this is the whole thing that we multiplied in. In order to find the new equation, however, of the sphere, you would do that to the old sphere. Another x over w.
W's at all.
That comes from the perspective transformation. You can't avoid that.
Well, you have a plane in 3 space, and you have a pyramid intersecting it in 4 points. There's no inherent w there.
If you looked at the spacings of the points where the eye pierces these things, they're not going to be equally spaced in real space because of the perspective. They're going to be a little bit farther apart towards the edges than they are straight in the middle.
That's right. I see. Yeah.
That's what happens when you divide by the w. W gives you that.
I see.
Okay. Now, there's several other random topics that I want to go over in the class. The only major thing that I want to talk about, and Ed wants to talk about, is texture mapping, which we won't do until next week or the week after that. I guess there's a tour next week. Partly because I have a whole bunch of slides which I want to show in connection with that I didn't bring with me this time. So there's some other aspects to the image making process that, little bits and pieces of things that I want to go into. In addition, I got several questions from hanging out in the terminal room this afternoon. Only time I get some feedback from the audience is to go and look over their shoulders when they're debugging programs. To talk about, and the major thing of that sort seems to be centered on color maps. So I want to say a few things about that. There are various interesting effects you can generate with color maps beyond what might be immediately obvious. And in fact, it seems that some of the people in here have not yet been really explained what a color map is and what it's good for anyway, so I should at least go through that. The idea behind color maps was originally invented, I guess, before it was cheap enough to make a full color frame buffer, so you could have 24 bits for a pixel, 8 bits of red, green, and blue. Ultimately, when you want to come up with a real color for a pixel, you have to have a number for red, green, and blue in order to feed the 3 electron guns that are hitting the screen of the tube. So there are 3 analog signals that have to come out of the frame buffer for each pixel. When you have a frame buffer that only has 8 bits per pixel, there's many different ways that you can turn this 8 bits into 3 different analog voltages. One of the simplest ways is just to wire the 8 bits into the D-to-A converter and plug the same values for red, green, and blue. So when you do that, the value 0 in the pixel comes out black, and the value 255 in the pixel comes out white, and numbers in between have various shades of gray in between. So this is just basically a black and white system then. Now if you want to get color, you have to somehow or other realize the fact that you are taking 3 numbers, which are really continuous numbers in the ideal physical space, and you have to somehow or other pack these 3 floating point numbers into 8 bits. And you can expect you're going to lose some resolution when you do that, but there are various ways that you can do it to minimize what you lose. Let's start out by assuming, say, that instead of a black and white image, like a white sphere, a white cube on a black background, that's what we get from here, we want to just make a red cube on a black background. And so what we'd like to do is to just plug the frame buffer number into the D-to-A converter for the red gun, so it gets intensities proportional to the number that's in the color map, and we want to set the green and the blue guns to 0. Well, the way this is done in general is to have this thing called a color map, which is basically just a table which is indexed by the frame buffer value. And that is when the electronics is going through to synthesize the image on the screen, it picks up a 8-bit byte of the frame buffer, and instead of plugging that straight to the D-to-A converters, it uses that as an index in this table. 256 entries in the table, numbered 0 to 255. Each entry in the table then has 3 numbers in it. 3 fields, basically, one of which is used for red. That field goes off to the red D-to-A converter. This field goes off to the green D-to-A converter, and this field goes off to the blue D-to-A converter. Right? Now these fields can be any number of different sizes. In the AED frame buffers that you have to play with, each of these things is 8 bits. So you're taking 8 bits into the table and you get 3 8-bit numbers out, which are 3 intensities for red, green, and blue. Now for just a red and black picture, what you would do is set up a table so that it has 0 in the red value and 255 in the bottom end of the table for the maximum red value, and just kind of linearly increasing steps going from 0 to 255 in here. And you put zeros everywhere in the table for green and blue. So any pixel value that comes in here, like 128 will come in, it'll pick up 128 for red, which gives you kind of a darkish red, and 0 for green and blue, and so you get a darkish red on the screen. Now, strictly speaking, when you set up this table, you need to do something a little more elaborate than make equally spaced steps here. You can't just go 0, 1, and 2, and 3 up to 255, because it happens that the electronics of TV are not linear. That is, the intensity that you see with your eye that comes out of the thing is proportional to the voltage applied to the grid to the gamma power. Gamma is a number. It's typically in the neighborhood of 2 or 3. And so if you plug in maximum voltage, 255 into this thing, you get a certain intensity. But if you plug in half the number in the table, these numbers here are proportional to voltage. They just plugged into D-to-A converters. Plug in half that number, 128. 128 to the gamma power is not going to be a half of what 255 to the gamma power was. It's going to be a quarter of it or something like that. So you have to do gamma correction in this table. Basically, you have to put numbers in the table which are the inverse of this function. So when the table lookup happens, this is all corrected for. Yeah.
Don't some units then have on top of the regular table, there's just a prom lookup table that gives you 12
There exists some hardware units that do have a two-step lookup table so that you will put linear intensities in the color map and they will translate to you. The trouble with that, however, is that you don't want to exactly put a prom in here necessarily because this gamma value changes. There's a little knob on the front of the thing called brightness, and that's what that knob does. It changes gamma.
But it's also true that if you're going to film, different color films have different responses, so you want to change your...
Yeah, the whole film problem is god-awful, and Ed talked about that a little bit. Basically, you like to retain flexibility within the program, I think, rather than burn it into a prom, because things change from day to day.
But if you only have 8 bits per color, you can get all sorts of jaggy steps, because that isn't enough.
The number of bits in the output end of the color map is a matter that's subject to debate exactly how many you need. The early Evans and Sutherland frame buffers, which I'm most familiar with, have 12 bits per color, 0 to 4096, 4095 for each of these things. And that's ample, but it might be more than you need. I mean, it's a little expensive having 12-bit DACs, but also it's a little bit of a data juggling problem because the numbers in the table are no longer fit into a byte. They have to have 2 bytes, and then you're wasting 4 bits because it's 12 bits instead of 16. But so that's a matter of perhaps even research as to how many bits you can really get away with before it becomes perceptibly obvious what's going on. One other aspect of this thing, however, is how the eye perceives light. The eye in the retina detects light not as a function of the intensity, but more as a function of the logarithm of the intensity. So the eye is a logarithmic sensing device, which means that if you take 2 different boxes of intensity A and B, and say this is twice what the other one is, so this is intensity of 1/2, this is intensity 1. You look at that and you say, okay, that's the difference in the intensity of those two. And then if you take a box of intensity, say 1/4 and 3/4, and you look at those are going to look a lot more different than these did. The intensity difference is the same. The intensity difference is 1/2. But this looks a lot brighter than this did, than this looks brighter than that one. It's the ratio of these two that the eye is interested in, which is a linear scale in logarithmic space. So that means that even if you take the intensity value 255 and 254 and put that up on the screen, say, boy, those look almost the same, and guess this is enough bits. That's not what you want to see. You want to take a look at the intensity value between 0 and 1, maybe in 2. And if you can see a step in there, then you know that you don't have enough bits. And I myself can almost see a step in 0 to 1 to 2 in the 4095 frame buffer. Just on the low end, your eye is real sensitive to that.
On the APDs, nothing even is visible on the screen if you have them that low.
Yeah, there are other aspects of that too. Basically put a ramp up there and take a look at the lower end of it.
So our programs are going to be generating all these RGB triples, but we can only represent 256 colors concurrently.
Okay, there's 2 aspects of
kind of sampling.
Yeah, there's 2 aspects of what goes on in the program. One is what you decide to put into the color map, and then how you encode the numbers into the pixels on the screen so that when they're looked up through the color map it makes sense. Right? So we'll go into that in a little bit in more detail right now. Let me make one global statement that for right now this gamma correction has to be done, but I won't explicitly refer to that from now on when I talk about yuck. Too much arm moving. When I talk about a linear ramp in here, I mean linear in intensity space, which assumes gamma correction is overlaid on top of whatever's going on here, right? Okay. Your program then is calculating a color image, which means that for each pixel on the screen, it decides it wants to have the red, green, and blue value be some number between 0 and 1, and various ratios of them that will add up to different hues and tints and whatnot. So we have 3 floating point numbers, basically, R, G, and B, that we want to display on the screen. You have to pack these things into an 8-bit value somehow. One way of doing it, which is one of the options on, I guess it is AED view, is to just divide this off into 3 fields. We'll say we'll pack the red value into the higher 3 bits, so that goes 0 to 7. The green value into the next 3 bits, which goes 0 to 7. The blue value in the lower 2 bits, which goes 0 to 3. And then a pixel value here will have packed into it then a complete composite of red, green, and blue. Now, how must you set up the color map in order to make this particular picture make sense? Here's the color map that goes 0 to 255 for the indexes of these things. Let's take a look first at just the blue column. What are we going to stick in the blue end of the color map? The blue end of the color map only wants to be sensitive to the lower order 2 bits, basically, of a pixel, which means that value 0 stands for a blue value 0, so we put 0 there. I'll just draw out the 2 bits for the blue field here. 0, 1 we want to map into kind of 1/3 intensity, and so we'll put, what's 1/3 of this? About 80? Something like that? 85, thank you. Good to have mathematicians in the audience. This should be 2/3, which I'll guess is being 170. And this should be 3/3, which is 255. I suppose it probably is more, it's not exactly 255, but that's close enough. Is it? Yeah. That's incredible. Okay. But you got your gamma correction, right? So that destroys it all. Anyway, so 0 comes out like this, 1, 2, and 3. And now, this is the first 4 elements in the color map. So you just repeat this over and over again. 0, 85, 170, 255, blah, 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 all the way down to the top. So we got this cycle of 4 numbers here just going over and over again. So anytime you come up with a pixel that gets plugged into this table, what will effectively happen for the blue end of things is it's only going to be paying attention to the lower order 2 bits. Whatever's in the higher order 2 bits will not affect it because this thing repeats over and over again. How about the green field? We want to make that sensitive to the middle 3 bits. More or less obvious thing here, except we have the thing shifted up. We have 0, 0, 0, 0. The first 4 of these things will be 0, because that's the lower order 2 bits of it that's really mapping out blue. The next 4 bits will be 1/7 of 255. Got them 34. 34. So you have 4 values of 34 going up here. And then the next 4 after that will be 4 copies of 60. What?
69, because it's actually 34 and 37.
Oh, okay. That stuff. Okay. And so on, right? And then the final column for red, we want to make that only sensitive to the higher order 3 bits. So we will now have 32 copies of 0 going in here, and then 32 copies of 34, etc. So this is a color map. Now this color map is already done for you, right, Dithering? Didn't do it like that?
We take a philosophical stand against low-resolution color maps.
Oh. This is a way that you might do it, however.
That will be in the program relatively soon, just that the problem is that the advanced version of the program crashed the operating system.
Good. Anyway, so if you want to make a full color picture, it'll be kind of grainy, but you'll get 256 different colors, and they'll be ranged out in the color cube somehow. Now, a useful way of looking at this is in terms of the color cube itself. The color cube being the coordinate space, red, green, and blue, and the cube formed by numbers going from 0 to 1 for each of red, green, and blue. And so down here at the origin is black. Up here at 111 is white, and the corners are red, green, blue, pure, and then the other far corners are yellow, cyan, and magenta, they're called, or the secondary colors and so forth. So any point that you can represent on the color TV monitor at some point within this cube, right? So a useful way of envisioning what a color map really does is to make basically a scatter plot in this cube. That is, for each number in this table, put a dot there. What's a black and white ramp going to look like? Equal values going from 0 to 255 in each of the colors. So that's just going to go like that along the diagonal of the cube. Equally spaced in intensity dots along the diagonal of this cube. So you don't get red and green and blue because the color map doesn't do that. This color map that we just did here with the 3, 3, and 2-bit packing of the red, green, and blue components will make a regular space grid kind of covering the whole space. There'll be 8 samples in the red and the green axis and 4 samples in the blue axis, but they'll be equally spaced grid of dots. And so in a sense, any particular point that you might find that you want to represent in RGB space, you kind of pick the nearest dot to that, and that's kind of as close as you can get, but it's, you know, as close as you can get. You only got 8 bits, you've got to lose something, right? So this is what that particular encoding would do. Now, another sort of thing that I can use it as an example, the Voyager simulation movies that I showed, I guess, the first day, were all done with an 8-bit frame buffer. And they took advantage of the fact that the colors that show up around Jupiter and Saturn don't have a lot of blues and greens and funny things like that in there. In fact, what I did was take some of the images that were sent back from the spacecraft and did a 2D histogram in IQY space to find out where the bumps were in the colors, and it turns out that they're all oranges, effectively, and whites. And so, if you look at that in the RGB cube, what the program does is to divide up the 8 bits into 2 fields. Uses 5 bits for the intensity, or the brightness of the color, and it uses 3 bits for the saturation of the color. And the color in question is orange. You only get one color, but you get various levels of saturation. So that means that for saturation 0, you're going to have 32 different intensity levels going from black to white here, which are the lower 5 bits of this thing. And so you're going to have kind of 32 dots going along the diagonal axis here. For saturation equals 7, which is the pure orange, which happens to be kind of right about there, it's 0.5 amounts of green and 1 amounts of red and 0 amounts of blue. So the RGB is 1 half and 0 of that. You're going to get another line of 32 dots like that. And for saturations in between there, you're going to get a thing like that. Now, when you calculate the picture, the pixel on the screen, you come up with the intensity that you like right here, and you kind of pick the nearest available pixel value, or nearest available color map value to that, and color it in. Now, some of the things about this that you have to be careful about is the fact that doing anti-aliasing or area averaging and so forth means that you're going to have to do continually encoding and decoding things into and out of this 8-bit space. There's a program, say, that puts the planet up. Another program, a totally different program, puts the rings on top of that. Where the rings overlay the planet, you've got already a pixel sitting there from the planet and another pixel for the brightness of the rings and some transparency ratio for the transparency of the rings in. So you're going to do an averaging operation between what's already there and the new value that you want to put in. So it's already there. You have to pull this and haul this out into a color space that you can do averaging in. This particular one is not good for that because it's a conical projection. Averaging really should be done in red, green, and blue space. And so to average these together, you have to take the 8-bit value out and convert it into RGB space, average those together, and then convert it back into the 8-bit space. There are some shortcuts you can take on that, but I won't go into detail on that. So this particular mechanism basically is saying we're going to have 8 different colors and 32 different intensities of each. Now for a little more lumpy appearance, you can get more than 8 colors here. You can have each of these little rays going off to a totally different place in the color cube. You can have 32 different things going from black to white, another 32 going from black to green, another 32 going from black to blue, black to orange, black to purple, and so forth. So you can have 8 different colors off of this. Where they start overlapping and merging together, you're not going to be able to average them together quite as nicely as you want to. But this particular technique is a fairly common one, and they're generally called tint color maps, and the number of colors is this. So this is a tint 8 color map. And you can imagine different allocations of bits between the intensity and the color, too. You can have 16 colors and 16 intensities of each one, so you have a 4-bit field and a 4-bit field. It's all just a matter of, 1, having your program encode the RGB into this 8-bit fashion, and 2, having the color map set up so that it decodes this thing into the 3 colors that you want to go onto the screen. Now, what other interesting things can you do with color maps? Suppose you wanted to draw an integrated circuit, something that I'm sure nobody here could possibly want to do. Integrated circuits are made up of different layers of stuff, and typically each layer has a color attached to it. And at least in the early days of integrated circuit design, they used to print these different layers on giant pieces of acetate with colored inks. And there was the green layer, which is the diffusion layer, something like that, and it would have all these green lines on it. And then there was another piece of acetate which had the polysilicon layer, which is typically drawn as red, and another layer of acetate which has the metal layer, which is typically drawn as blue. And in order to see if these register, you just stack them up on top of each other, and you put them on top of a light table, and you look at it, right? So you have green showing through here, and red showing through here, and blue showing through here, and every place where there's nothing that's white, all the light comes through. You can simulate the same process in a frame buffer by allocating 1 bit of a pixel to each of these layers. So for a particular byte on the screen, you might say the low order bit is going to be turned on if there's a green thing there. The next byte is going to be turned on if there's a red thing there, and the next byte is going to be turned on if there's a blue thing there. We just deal with 3 layers for the example right now. And so you can easily overlay these things one at a time by having the program which reads in the layers from SIFplot or whatnot go through and just orient the bits appropriately as it comes up with a green or a blue box. Now what we'd like to do then is to have this byte value be transliterated into the proper intensity show up on the screen. So here's the color map table again. Where all the bits are 0, it means there's nothing else we want white to show through. So we put 255 in all those slots. This is kind of the reverse of what you typically think. Typically you think 0 is black, but in this case 0 means nothing's there, so light's shining through. For 0, 0, 1, that means there's just green, like that. For red, that means there is just red. And if the green and the red overlap each other, you want to get some sort of darkish brown color, say, to indicate that there's an overlap between green and red. So you put maybe 128, 128, and 0 in here, something like that. And for the blue layer, 00, 255, and where blue and green overlap, you want to get some maybe turquoise, and so you come up with 128, 0, 128, so forth. So you set up the table like that so that it transliterates the bit pattern in here into stuff. The cute thing about this is you can now shut off these layers one at a time just by stuffing new numbers in the color map. That's real fast to do, right? There's only 256 times 3 numbers in the color map. You can blap that in there easily in an inner frame time. You don't have to repaint the 250,000 pixels on the screen. If you want to just look at the blue layer now, you just set the color map up so that the red and the green is always set to 0 and the blue is just on and off at the appropriate time. Suppose you want to do something maybe slightly different from this, which is you want to draw a bunch of polygons here that overlap each other in various ways. And you want to have certain of them appear to be in front and other of them appear to be behind. You can allocate a bit for each polygon then, if you only have 8 things on here. So This polygon would be the bit, let me just deal with 3 bits worth of frame buffer value right now for expository purposes. So this polygon here would be the bit 001. Out here where there's nothing, there's bit 000. In here, there's bit 010, that's this polygon. Where they overlap, both the bits are turned on, like that. And this would be 100. Where these overlap, it's that, and where these overlap, it would be like that. And we want to have this triangle appear to be in front. So everywhere where the lower order bit is turned on, we want to have that mapped into the color of that triangle. So you set up the color map table so that everywhere where the lower order bit is set, which is kind of every other element, has the same set of numbers in it. Orange, say. So you put orange into all the odd numbered slot, well, all the even numbered, odd numbered slots in the table. This you want to have the next one back, and so everywhere where this bit is set, the second bit is set, but the first one is clear. That will be in these elements here. Every fourth element, you make that purple, say. Similarly, this will be the farthest one back, and so you put all the ones you haven't set yet, you set those to chartreuse, whatever. So now these things will be in order. Again, you can change the order of these things by just stuffing new numbers in the color map. You can make the orange one pop into the background, everything else pop out in front of it. And this turns out to be handy for some things. So you wind up starting to get into the game of what's called color map animation. Oh, tape change. Okay, let's wait for tape change.
We need a picture jumper out.
I can imagine. Okay, color map animation. This was pioneered by a guy named Dick Schaub, who was working at Xerox PARC at the time, and he kind of built one of the first ever frame buffers with a color map on it, and played around with some of the various tricks you can do by sticking an interesting, a particular pattern of numbers in the frame buffer memory itself, and just tinkering with the color map to make the picture change. One of the simple ways of doing that is to say, suppose we want to have a ball bouncing. Classic example in computer graphics. Everybody has to make a ball bouncing. And we want to show this thing going boink, boink like that, right? Now, as long as these things don't overlap, we're in good shape. We make this background be value 0. This will go 1, 2, 3, 4, 5, 6, and 7, right? These are the numbers that are in the color are in the frame buffer now. We set that up once. Now we set up the color map. 0, 1, 2, 3, 4, 5, 6, 7, etc. When we want the ball in position number 1, we stick zeros everywhere in here except slot number 1. We put 255s in there to make that white. So this and this and this and this will all map to black as well as the background. For time step number 2, you stick zeros in slot number 1 and you put 255 in slot number 2. So this now maps into white and all the rest of them map into black. And so forth. You just kind of shift the white down the table, and so this thing goes bouncing by. So as long as these things don't overlap, you're in good shape. If they do overlap, you can get away with it if you start allocating bits to it again. You can have 8 different pictures in here for eight totally different bit planes. You can have 8 totally different pictures in here, black and white pictures, and shuffle back and forth between them by just sticking the appropriate numbers in the color map. And once you kind of get the hang of it, you can start inventing all sorts of interesting tricks you can do. Some of the nicer effects that I've seen, Dick Schaub, and he has a real good artist who's really tuned into the system named Damon Rary. They've got a scene, say, a lot of it was done for the Pioneer Venus probe, just animated graphics, slides that actually have a little bit of motion in them. So they had various things with little labels and pointers to what's going on. They turn on the labels kind of one at a time by just stuffing the right numbers in color map. Now, in addition to just having them pop on instantly, you can make them slowly fade up by having the two contents of color map kind of interpolate from one to the next. Most of the values stay the same, but the values that you want to change have it change slowly by a small amount for several different frames until it's built up to the new value. So you can fade these things up. Another really nice effect was showing the solar wind here. And that is done by having the background picture put in here and then allocating values, say 0, 1, 2, 3, 0, 1, 2, 3, and so forth, having little boxes of numbers 0, 1, 2, and 3 in here, like that, where the values 4 through 255 are used for other purposes for the background, so those don't change. And then you just cycle the first 4 elements of the frame buffer, of the color map, change those around, leaving the remainder of them the same. So most of the picture stays the same, but you get this really nice effect of stuff flowing along here to show the solar wind. And there was another one I did showing cloud patterns, and the artist had to be really good to do this, but the one thing that really impressed me was the surface of Venus, and then he used a kind of a stipple paintbrush, a lot of little clustered dots here like that. And he did it in such a manner so that when you cycle the first 4 or the first 8 elements of color map, you would see it looks like the clouds are zooming along like this, where the ground stays fixed, but you can see clouds in front moving faster than the clouds behind, which is real classy. Okay, what other games can you play with the color map? Well, may as well at least mention the old tried and true thing. Suppose you have some picture of whatever random type you've got in here, and you've got a color map with a whole bunch of bright colors in it in some weird order. If you take each slot in the color map and you move it down by 1 and take the bottom contents and move it by 1, if you just rotated the contents in here, everything seems to shift by, the interpretation of each pixel shifts by 1. And so you keep doing that and you get these patterns go squish, squish all over the screen. This is called psychedelic pictures. There's one other cute trick that I stumbled across at Utah, which is, suppose we want to draw a sphere here, or some arbitrary polygonal object, and we would like to experiment with light reflection models. We want to be able to change the proportion of ambient to reflected light and the direction of the light source and so forth. Rather than putting an intensity in each pixel on the screen, what we will do is encode the direction of the normal vector into 8 bits. And so what I did actually, I think I did it sonically, but it took the normal vector with just the x and the y components of the normal vector. As soon as this thing is normalized now, so the z component is sort of implicit in what the x and y's are. And you can take the x and y either and pack that into 4 bits each for the x and y component, or else you can do it into circular coordinates. If you take the x and y and take, here's the plane here, and here's pointing straight at you, and if you take the this angle here that is tipped away from you, and then the angle that it's rotated around, you just turn this into spherical coordinates, you get a little bit better use of the bits. And now you have 256 different normal vector directions that you can represent. And so you make a table of normal vectors, and now you can have a little program that takes the tablet and recalculates the intensity for each of just 255 different polygons, stuffs them in the color map real quick, and so it's kind of like shining a flashlight on this object. You can move the light source around, or you can hook up to knobs. You can change the specularity or the matness or the hue or whatever this thing. It's a nice thing for generating the sets of parameters to feed the lighting model to make the real picture. You get a kind of an impression of what the thing's going to look like this. You can make a polygon tiler for that matter, that as long as you had 255 polygons or less on the screen, would tile them in and just allocate a frame buffer number for each polygon, keep a table of what the normal vector for that polygon really was someplace else. Then you'd have a real accurate picture of what that polygonal picture would look like, and you can change the lighting on that. For the encoding the normal vector thing here, of course, you're going to get some granularity in it because you only get 255 elements going across the whole sphere, so it looks like it's tiled with a whole bunch of little polygons. But as long as you're dealing with flat polygons and you only have 255 of them, you can have a whole different normal vector for each one. You just have to keep the table around in between generating the image and generating the color map. So those are some of the tricks that you can do with color maps. Trying to think if I missed any. that's basically it. The one thing that I want to talk about then briefly on top of that is a process called dithering. And that has to do with something that you've seen already with the Versatex. Suppose you have a display device that has less bits of intensity than you would like to have. You'd like to have at least 8 for each pixel on the screen, but suppose you only have 3, like for this red, green, and blue encoding scene. You have only 3 bits of intensity for the red picture, or 5 bits of intensity for if you use the 10/8 sort of color map. The idea behind dithering is that you're going to trade off intensity resolution for spatial resolution in your picture. Instead of having, strictly speaking, 512 pixels across with only 8 different intensity levels, you're going to get the effect of having maybe half as many pixels across, but more intensity levels. And you do that by spatially scattering the on and off pixels in such a manner that if you stand back from the picture, like a little checkerboard of on and off pictures will serve as a medium gray rather than just on and just off. So the easiest way to talk about dithering is to deal with just a 1 bit per pixel picture, which is what happens with the Versatech. And so we're just going to go on or off for the pixel. Now suppose we have a plot here of desired intensity. And actual intensity. And we make a linear ramp here. We want to make a ramp going across the screen from black on the left edge to white on the right edge. Now if we've only got 1 bit per pixel, the actual intensity is either going to be 0 or 1. Right? And so typically what you'll do is have that sort of approximation to the intensity profile on the screen, which means that the left half is going to be dead black and the right half is going to be dead white. Well, what dithering basically does is say, for this particular pixel here, we want to have a gray value of, say, 0.6. Rather than just threshold it, anything above a half gets white and anything below a half gets black, we'll say, let's do a little probabilistic thing here. The easiest way to do is to say, let's toss a dice. Pick a random number between 0 and 1. If that number is above 0.6, we'll color it white, and if it's below 0.6, we'll color it black. So we're adding some noise here that's kind of half the distance between pixel values. So that means that down here we'll have the probability of making this pixel white will be 0.1, so these will probably be still black. When you get to this point, you'll have, every now and then you'll start having a white pixel. When you get up to this point, the pixel will be half white and half black, 50% chance. When you get up to this point, 3/4 of them will be white and 1/4 of them will be black. And so you get this checkerboard effect across the screen. On the left-hand side it's black, and you get more and more white pixels until you get to the right-hand side of the screen, you get all white pixels. You stand back for a little bit, and it blends together fairly well in order to give you a better gray tone than you would get by just thresholding. Now there are various ways of optimizing this thing. The random number generator approach is not too bad, but you have to call a random number generator for each pixel. Another way that you can do it is to do what's called ordered dither. And that is you pre-specify for each pixel a little threshold value. And I want to start dealing in binary numbers because they're going to be more easy to deal with. So instead of numbers from 0 to 1, I'm going to go 0, 1, 2, and 3 here. The upper left 2x2 chunk of pixels on the screen have these 3 numbers attached to them. And then you just kind of replicate that over again. 0, 2, 3, 1, etc. down like that. Now what this does is when somebody hands you a pixel value, you multiply it by 3, so you get a number between 0 and 3 instead of 0 and 1, and you compare it with the threshold that's kind of built into that picture element. If it's above the threshold, you color it white, and if it's below the threshold, you color it black. So the ordered dither means that you're going to get a uniform pattern in here for half black, for medium gray. If you hand it the value 0.5, you're going to get half these pixels on in a regular checkerboard pattern and half of them off in a regular checkerboard pattern. So that's why it's called ordered. Now this just splits it up into you only get 4 effective intensity levels out of this thing. In order to get a finer detail of this thing, you kind of recurse on this particular pattern, which means you turn this into a 16-element pattern. The upper left-hand corner has zeros in it. I'll write these things in binary now. The upper right has 1, 0, 1, 0, 1, 0, 1, 0. This has 1, 1, 1, 1, 1, 1, 1. Like that, to make the large 2x2 blocks, and then the lower order 2 bits of the pattern have a copy of what you had originally here. So this has got 0, 0, this has got 1, 0, this has got 1, 1, this has got 0, 1. I don't know if there's a good way of explaining this, is to just demonstrate it. But this gives you a set of patterns here going from 0 to 15, basically. And so now you have a threshold, you take the number from 0 to 1, you scale up by 15, and then compare it with the threshold, and you get 16 different gray levels in this. So that's ordered dither. That's similar to what you're using on the Versatech, with one difference, which I will, I guess, mention right now. Often it's the case, as in the Versatech case, that you have a display device which is it's got more spatial resolution than you have in your picture. You're calculating 64 by 64 element pictures. The Versatech has, what, 2,000 or 3,000 spots going across it. And so the easiest way to do that is to come up with macro pixels, basically. 16 by 16 array of Versatech dots equals 1 pixel that you're calculating. And you'll set up these patterns of macro pixels according to this ordered dither matrix. And you'll just have one pattern in here, so that intensity 0, they're all turned on. And maximum intensity, they're all turned off. Halfway intensity, they're half on, half off, etc. And so you just kind of replicate these pixels and stamp them down as rubber stamps when you come up with the pixels. Well, that is good for debugging programs, but that's not really the right way to do it because of several things. One of them is perception, again, of a picture as being a sample of some ideal picture. Ideally, you have this function of x and y space on the screen. It's some smooth, continuous function, right? And you're just sampling it at equally spaced intervals to put up on the screen. Now, assuming you've done all lift filtering and aliasing and so forth, once you've sampled this thing, you say the intensity at this particular microscopic mathematical point is less than so. You don't then color in an equally intensity box around that, and you don't color an equal intensity box around that and then around that. The real picture that you want to display is some interpolation or some smooth curve through these intensity values. A simple way of doing this is just bilinear interpolation in this case, since it's two variables. You can get more elaborate if you want to, but the way that you should really display one of these 64 by 64 pixels on a Versatech is to imagine the 64 spots here and 64 spots here. Then as you go across one scan line on the Versatech, you do linear interpolation between the intensities on that particular scan line to give you at least a more smooth function. And then for each of these Versatech spots, you compare it with the threshold, which is going to take this thing here and replicate it lots of times because we've got a couple of thousand pixels. Compare it against its threshold, and you'll get a much smoother blending of one pixel to the next here. So each Versatech spot itself has its own threshold. It's not a whole 16 by 16 block of them that has a threshold. And this will smooth out the things considerably, and this will improve the picture a lot. This happens a lot. Versatech is a very common example. There are other sorts of output devices that are used for this. Yeah.
There's one of the complications with the Versatech, which is due to charge spreading, that a dot next to a dot is not the same as a dot next to a dot.
Right, that's kind of the next thing I was going to mention. The fact that on real devices, two consecutive dots are not necessarily bilinear interpolation in this case, since it's two variables. You can get more elaborate if you want to, but the way that you should really display one of these 64 by 64 pixels on a Versatech is to imagine the 64 spots here and 64 spots here. Then as you go across one scan line on the Versatech, you do linear interpolation between the intensities on that particular scan line to give you at least a more smooth function. And then for each of these Versatech spots, you compare it with the threshold, which is going to take this thing here and replicate it lots of times because we've got a couple thousand pixels. Compare it against its threshold, and you'll get a much smoother blending of one pixel to the next here. So each Versatech spot itself has its own threshold. It's not a whole 16 by 16 block of them that has a threshold. And this will smooth out the things considerably, and this will improve the picture a lot. This happens a lot. Versatech is a very common example. There are other sorts of output devices that are used for this. Yeah.
There's one of the complications with the Versatech, which is due to charge spreading, that a dot next to a dot is not the same as a dot next to a dot.
Right, that was kind of the next thing I was going to mention. The fact that on real devices, two consecutive dots are not necessarily disjoint. The Versatech things tend to make them overlap, I think even by a factor of 2. So that means if you make a checkerboard of these things on and off, you're going to get dead black just about. Maybe a few little cracks in between here will show through, but you're going to get elbow dots then. Now there's some ordered dither patterns that have been come up with for that. I'm not familiar with the most recent hot news on it, but one of the ways that this happens is to use sort of a newsprint style dither matrix, and that is you set up your dithering pattern, something like this. Let me just draw one 4x4 square. For the old ordered dither, each square has a number in it. And for this thing, each square is going to have a number in it as well, but they're just going to be assigned differently. Like that. So that consecutive things are next to each other. And this is called a newsprint or a halftone dither because this tends to make larger or smaller halftone dots similar to what the halftoning process in newsprint is. Now this, as intensity increases, this thing's going to make a dot that gets bigger and bigger and bigger until it fills up the blob, which is not exactly the way halftoning works because they have a process where the blobs then start merging together to make smaller and smaller white space in between. So in order to do that, you make 4 of these things, elbow to elbow, and you go up here to 15 like that, and then you keep counting 16, 17, 18, 19, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. So the spiral goes out like that and then starts filling in the gap in here. These two are the same except flipped around the other way. So you have two 16 on the squares going from 0 to 15, then 2 other squares going from 16 up to 31. And so this gives you an intensity scale with 31 different brightnesses in it, basically. If you imagine the whole screen is black in at one intensity, you can kind of visualize what the shape of the pattern is going to be. If you want to make the whole screen be half intensity, that's value 15. And if you compare all these things, you get alternating black and white boxes at about newsprint style resolution. Now note that these boxes are Versatech boxes now, and so they are the interpolated pixel values from the original data. And so for one scan line, you interpolate in between there. As you go down one scan line, fill in the gaps in between 2 scan lines of real data, you have to interpolate in the y direction as well. And so in a sense, the number of pixel dots here is decoupled from the number of dots you start out with. Quite often they'll be integral multiples of each other, but that's not necessary. There are 2 other dithering functions, which I'll mention real briefly. One of them I find is very amusing, but turns out to be not the best kind. And I believe the name for this is called MASIC. Where that comes from, I have no idea. But again, it's a mechanism for coming up with 16 numbers to serve as the pattern that's going to be replicated over and over the screen for the thresholds for the dithering, right? What they've done here is say, well, what we'd like to do is to have it so that, if you imagine this pattern replicated over the whole screen, you take any random 4x4 chunk of the screen, and we want to have the pattern that's generated by that be about the same. We want to have kind of an equally spatially scattered high and low values here, sort of what you'd like. So what they did say, let's make this matrix a magic square. Magic square is a matrix so that each column adds up to the same number, each row adds up to the same number, and the diagonals add up to the same number. Now, if each column adds up to the same number, if you move down by 1 pixel, so you have the top thing of that and the bottom thing of this, you're going to get the same number. So each cyclic shift of a magic square is another magic square. And so this gives you a nice even pattern of distribution of things like that. So here's an actual engineering application of magic squares. It works pretty good, but it's maybe not the best one, unfortunately. The other one is called minimized average error. Both the MASIC and the minimized average error are good for, mostly for things where the pixel dots are disjoint from each other. If they overlap, then it kind of craps up the effect. Minimized average error is based on the desire to make it so that if you take and dither your picture, so we've got on and off dots here, and if we take a particular pixel and we do a weighted average of the original picture with some, Gaussian fill or something like that, 2 or 3 pixels across, and we come up with the average value for that. And if we take that same weighting function and place it over the dithered picture, so we're taking a weighted average of that. Now the dithered picture is just going to be zeros or ones here, but the weighting function can be continuous values in between. So the area averaged dithered picture is going to be some floating point number, and the area averaged original picture is going to be some floating point number. What we want to do is to pick the pattern of zeros and ones, which cause those area averages to be as close as possible to each other. Sort of makes sense. When you stand back from the picture and build up a little bit, we would like the colors to run together in the appropriate way to do that. Now the trick, however, with that is that it sort of requires that you know the answer before you can find out the answer. In that, if you imagine kind of solving for the ons and offs here in order to make the weighted average of the original picture match up with the dithered picture, you wind up with, an equation of 256,000 unknowns or something like that. So typically the way this is implemented is to do it in a scanline fashion and do it in a manner where the weighting function is really only the upper left-hand portion of the picture, and the appropriate weighting elements are either maximum centered here and it trails off to 0 like that. You haven't computed these yet, so you don't include those in the weighting function. So you assume that you've computed all the upper scan lines and the left scans already, and you want to figure out whether to turn this one on or off. So you make a weighted average of the other pixels like this, what's really there, what you really want to show, and what the dithered pattern is. And this gives you essentially an equation to solve for this in order to give you the closest value of, make it 1 or 0, whichever of those two gives you the area average weighting closer to the real picture is the one that you pick. And you just shift over by 1. This requires a bunch of buffering, however, of the scan lines and so forth. So this is a bit slower and a bit trickier. But this, for my mind, just visually makes the best looking dithered pictures.
Yeah. Try putting your bicycle in the best they can.
Quite possibly you could, yeah.
As it turns out, though, if you drive the vertex of these things too slow, if you're driving in real time as opposed to buffering the binary dot, it goes at different speeds as the algorithm gets swapped into that, it still makes the picture.
Yeah, there are all sorts of practical considerations with dithering that kind of make a lot of these things lost in noise, but in a certain sense, if you have hardware that does garbagey things to you like that, starts and stops and smears across the picture, you're out of luck. You have to wait until the end and get rid of all the people and get the picture.
When did you want our programs? Holiday Monday, field trip Wednesday, so...
Assignment number 4 is something like June 3rd, I mean, right?
Oh.